All right, everybody, this is your uh, water and solutions review. Your test is going to be on Friday. So here we go. What is a nonpolar molecule? A nonpolar molecule is a molecule that has an even distribution of electrons with the molecule. So there's no real pole from either end of the molecule. There's no big strength in either direction. Number two, what attractive force do nonpolar molecules have? They have a force called the London dispersion force. Pretty weak force. Polar molecule. A polar molecule is a molecule that has an uneven distribution of electrons. Distribution of electrons. I'm going to put a little abbreviation there with the molecule. There is a pole. Is a pole in one direction or another. And what that does is that creates a positive and a negative end to the molecule. Positive and negative end to the molecule. The attractive forces, number four, the attractive forces that polar molecules have. Polar molecules have attractive forces that are called dipole, and one you're familiar with, hydrogen bonding. Okay. Number five, we're ranking these intermolecular forces from strongest to weakest. Strongest being the hydrogen bonding. Like, that's why water has such a high boiling point. Dipole is next. And then the weakest is the London dispersion force. Oops, dispersion, we get that looking right. London dispersion. Okay, in that order. So strongest, strong, and the weakest. Okay, and strongest and weakest. What causes a water molecule to have high boiling point? It has a high boiling point due to the hydrogen bonding. It takes a lot of energy to get those bonds to be broken. Surface tension. If you give an example of surface tension, we talked about this before. You've seen this stuff before. A bug sitting on top of water, on top, not floating, but on top of water, a pond, we should say, maybe a leaf, the same kind of thing, Okay. Number 8, define the following complete sentences with examples. Okay, so we'll see if we can get complete sentences out of this today. Cohesion. When, let's say, water can stick to itself. When a molecule pulls into itself. So when water sticking to itself, and we've used that definition before. And I don't really care about the complete sentences. Adhesion. When a molecule sticks to other surfaces. Water sticking to other surfaces. You can come up with numerous examples for both of these. Okay. Viscosity. The resistance of a liquid to flow. Okay? All right, so let's go down here. List 3 factors that cause a solid to dissolve more rapidly. One is by stirring it. The other term for that, or if you're going to shake it, shaking, that's called agitation. All right. Another one is if you increase the surface area, then it will dissolve faster. Surface area of a solute, or solid. And then the third one, if you increase the temperature. I think most of you are most familiar with the first one and the third one. Stirring, shaking, which is agitation, increased surface of a solid, and increased temperature. Okay, let's move on. 2 factors that affect the rate of gases dissolving in a liquid: pressure and temperature. So, in order for a gas to dissolve faster into a liquid, you have to have a higher pressure and you have to have a lower temperature. We talked about that cold soda pop. The colder the soda pop or the colder the seltzer water, the easier it is for the gas to dissolve in the liquid. And the greater the pressure, the same thing. If you decrease the pressure, like if you open a pop can, it's going to go flat in a matter of what, half an hour, something like that, or even sooner. Okay, solvent. All right, the solvent is the substance in the greatest amount that does the dissolving. And we use that universal solvent, water, as an example. So we call it the universal solvent. It can dissolve so many different things. And that's, about between 70 and 80% of Earth is covered with water. About 60% of our body is made up of water. Okay. So water and alcohol is another one. So we had water and alcohol. Okay, like rubbing alcohol. We tried that one. A solute is a substance in the least amount that is being dissolved. And all of you have had some practice with this at some point in your life. Salt in water is an example of a solute. Sugar in water is an example of a solute. The water is a solvent. So go straight on to saturated solution. Saturated solution, the maximum, I'm going to abbreviate MAX, the maximum amount of solute that can be dissolved in a solution. Okay. And we're going to abbreviate solution, SOL''N. Just makes it a little easier to write. There's got a cat eating my foot. Get away from me, cat. Okay. All right. So that's like when we looked at on the line, when we looked at the solubility curves, if it's on the line, that's called saturated. Unsaturated is a solution, and I'm going to abbreviate SOL''N, that can hold more solute. And that was under the line on the solubility curve. And then supersaturated, the solution, let's see, is a solution that contains more solute that it can hold. And that's when you see, like, when you're trying to make Kool-Aid or something like that, and you see a bunch of sugar in the bottom, no matter how hard you try, you still have that sugar laying in the bottom of the container. And that was above the line on your solubility curve, your solubility chart. All right. molarity, the number of moles per unit volume, okay, or liter of solution. So really it's moles per liter. Okay, that's your equation for molarity. And so we write it again. M is molarity equals the number of moles, and I use the number N. I'm just going to use moles, and I'll put the L right there. I used the N before, and then I used the liter before. So that's what you're looking at. An example of that is like saying, okay, we've got some really concentrated hydrochloric acid in the lab, and we're calling it 6 molar hydrochloric acid. Or if we have a really low concentration of one, we could say, and this is a high concentration, by the way, compared to, say, something like 0.5 molar, which would be a low concentration of acid, okay? And so now, let's go to the solubility chart. If you will notice on the solubility chart, and here's a trend that you'll have to know for your test, that most solids increase their solubility with an increase in temperature. Okay, that's important. That's going to show up on your test, and this may show up on your test this may show up in test. I don't know if for sure or not, but some or most gases. I'm going to say most gases. Gases tend. Let's put it that way. Gases tend to increase their solubility with a decrease in temperature. So the colder your pop gets, the more carbon dioxide can be dissolved in it, because that's what the carbonation is. Okay, so let's use the solubility chart and take a look at what's going on. Number 12, how much potassium nitrate will dissolve in 100 grams of water at 40 degrees C? So we're going to go to 40 degrees C. And dissolving means that's going to be on the line. So write that down there. And so we have to go up to the line of KNO3, which we go all the way up here to KNO3, right about there. And we go over here, and that would be 60 grams. Okay, pretty easy. At what temperature will 70 grams of potassium bromide completely dissolve? So now we're going to do the opposite thing, and we're going to go to where potassium bromide is, and 70 grams of that, and that'll be on the line again. All right, and so 70 is going to be right about here, and so we're going to go all the way over to potassium bromide, and that's the line right there. And that's going to be 30 degrees. Well, hold on. Is that 30 or 20? 70. That looks like 20 degrees to me. No, 30 degrees. 30 degrees Celsius. 30 degrees Celsius. It'll completely dissolve at 30 degrees. Unless I did something crazy. Nope. I think I'm right. Okay. There we go. If I'm wrong, then somebody will tell me. Okay, so determining if the solutions are saturated, unsaturated, or supersaturated. The first one is 160 grams of sodium chloride dissolved in 100 grams of water, 20 degrees Celsius. So 160 grams, so you have to go to 160 grams of that. And I'm going to erase those other ones really quickly so we don't get confused. But if you go to where 160 grams of sodium chloride is right there, and you go to where it is at 20 degrees Celsius, which is right here, and you go straight down, that's going to be above the line, because that's sodium chloride right there, and that's going to be super saturated. Okay, it's above the line, so I'll put above right there. 20 grams of sodium chloride, so we start at 20 and we go to 80, and here's 20, Oops, I want that. 20. We go to 80, and it's way over here. And we go down like that. It's below the sodium chloride line, so that's unsaturated. And that's below. And then the other part is 110 grams of potassium nitrate dissolved in 100 grams of water at 60 degrees Celsius. 110 grams of potassium nitrate. So we go up to 100 first, okay, right there. So we go to 80 all the way over. And that's right there. And see potassium nitrate. This is the line for potassium nitrate. It's below that line again. Oh, or is it on the line? You say 80 or 60? Oh, 60. Excuse me. Oh, no. That's 60, not 80. So at 60, it's actually right on the line. Okay? Or close to it. All right? Oh, 110. There we go. 110. So it's, there we go. 110. There we go. Now I'm straightened out. Okay. So at 110 grams, we're going to say that's saturated because that is on the line. Okay? And so that is part one of this review. We're going to solve molarity problems, number 17 to 20 on Thursday. So this is ready for tomorrow. Hope this helps.